The homework assignment is due tonight. So let me know if you need help with any problem before we go to the next chapter. YouTube, right? Is it running? Okay. Good. How many people? 4 people. Okay. Okay, so if you don't have questions about the homework assignment due tonight, we're going to start with chapter 19. And chapter 19 is the chapter that requires more attention from you. And it is going to pay off because based on chapter 19, the concepts of electric potential energy, based on those concepts, we're going to develop the following chapters related with electricity and eventually with magnetism. So pay attention, spend the time with chapter 19. I would study the chapter carefully more than once. 5, 6 times, it is going to be beneficial. Every time you read the chapter carefully, you're going to find new details, and you're going to encounter, of course, confusing statements, which you have to bring here in class, and we're going to discuss them. Okay, so so far we have Coulomb's law, which describes the force that appears between 2 point-like charges. Notice that in Coulomb's law, we need to take the product of the algebraic sign of the electric charges in absolute value. So minus signs don't count in that problem. And the reason is that the formula written this way just describes the magnitude of the force between 2 point-like charges, not the direction. Based on Coulomb's law, of course, the constant of proportionality, don't forget, is expressed in terms of electric permittivity of vacuum. But based on Coulomb's law, we define the concept of electric field at some point in space. And that definition was based on the force that would act on a point-like charge Q placed at that position. And the definition for electric field is like this. So basically, the electric field is force per Coulomb, force per unit charge. Using Coulomb's law and definition of electric field, we discovered that the electric field created by a single point-like charge at a distance r from that charge is given with k times charge in magnitude again divided by r squared, where r is the distance from the source. This is the electric field from a single point-like charge. The direction of that electric field again described with words usually. After that, we defined the concept of electric flux through certain area. And based on the concept of electric flux through certain area, we wrote Gauss's law. So we defined electric flux through certain curved surface as a sum of a small piece with area A of that surface multiplied by the electric field that goes to this small piece multiplied by cosine of the angle between the normal to that small piece of surface and the electric field going through it. Angle phi subscript I, let's say, and do the summation, and you have the total electric field. So, based on the concept of flux, we wrote the first Maxwell equation, which says that the electric flux that goes through any closed surface is equal to the total charge Q enclosed by that surface divided by electric permittivity of vacuum. Based on Coulomb's law and, well, Maxwell's equation, Gauss's law that I just wrote has physical content equivalent to Coulomb's law. But Gauss's law, the first Maxwell equation, is more convenient for calculations. And we did two simple calculations for which you just have to know the results. The first calculation was a calculation about the electric field created by two very large, uniformly charged flat plates. One of them charged with positive, the other one with negative electric charge with equal magnitudes but opposite signs. Then we want to know the electric field between them. And the result of that calculation was that the electric field in the space between the two charges, between the two plates, is equal to the surface charge density of one of the plates in magnitude. Again, divided by the electric permittivity of vacuum, if the space between the two plates, of course, is filled with vacuum or air. Air is almost the same electric property as the vacuum. So this was one of the results that can be easily derived from Gauss's law. The second result, also very important, and actually it makes our life easier. It says that the electric field created by a charged spherical object, uniformly charged spherical object, is given with the same expression as the electric field created by a point-like charge located at the center of that spherical charge distribution. So for you, the electric field is equal to K times Q, again, in magnitude, divided by R squared. And we're talking about the electric field outside that charged, uniformly charged sphere. So no difference between this and this. In other words, if you think of the electron as a uniformly charged sphere, the properties, the electric field properties are exactly the same as if you think about the electron to be a point-like object, mathematical point at the center of this electron. So we just cannot distinguish the two cases. Well, chapter 18 starts with the introduction of the concept of electric potential energy. It is a simple concept, but we have to be careful with it. So look, in the case of gravity, we introduced gravitational potential energy of an object at some position close to the surface of the planet as mgh, where h is the height of the position of that object. M is the mass of that object. And the way we reached that formula, mgh, gravitational potential energy was mgh. The way we reached this formula was by calculating the work done by the gravitational force mg acting on a mass m. located at certain height. So here is the mass. The gravitational force makes this mass move, cover some distance, use the definition for work, and you're going to get that the work done by the gravitational force is equal to the difference of two terms that look like mgh. Mg initial h minus mg final h gives you the work in magnitude. Well, since the electrostatic forces are so similar to gravitational forces, we can use exactly the same procedure to invent the concept of electric potential energy. But there are some technical difficulties in the case of electric forces because the gravitational force close to the surface of the planet is constant, mg. Well, the electric forces change as the square of the distance between the two charged objects. So we can use exactly the same procedure, but mathematically we have to do some integration, differentiation. Integration basically is what has to be done mathematically, and this is not a calculus-based course. So in the textbook, we say that, well, calculating the work done by the electric force when, let's say, you have one charge right here fixed, pinned down at this spot, and the other charge is allowed to be attracted or repelled. The calculation of the work done in the process of, let's say, this attractive force moving the charge from here to here, doing exactly the same calculation, you reach the conclusion that the work done by the electric forces is again a difference of two terms, and those two terms are going to look like this. Like, so electric potential energy is going to be equal to A times the first charge times the second charge divided by the distance between them. So this is how you get this result. Again, in the textbook, they just give you the result for electric potential energy. And notice how similar this formula is to the formula to this one. Right? It is pretty much the same, but there are differences. The distance between the charges is not squared in denominator, right? And the second important difference is that the formula for electric field, you use the value of the electric charge in magnitude. While here, the electric charges have to be taken together with their algebraic signs. So if Q1 and Q2 have opposite algebraic signs, the electric potential energy of that system of two charges is going to be a negative number. Now, working out the units in this formula, you can demonstrate, well, we cannot do it yet because our definition for Coulomb is going to come later on in the next chapter. But if you trace the units, you're going to, of course, discover that electric potential energy, like any other energy, is measured in what? Joules. Yeah. Nothing else but joules. So now, with the introduction of the concept of electric potential energy, let's write down all types of energy that we have encountered starting from the first semester. Gravitational potential energy, unfortunately, only for the case of an object that is close to the surface of the planet Earth. But still, it is most of the objects around us are close to the surface of the planet, so it works. What other kinds of energy have we encountered so far? Yeah.
Elastic potential.
So elastic potential energy is 1/2 k times x squared. And k here is a different k. I'll write it like this, different k. Spring constant in this formula, elastic potential energy, k is spring constant. X is the displacement of the spring end from its equilibrium length. So if the spring is not extended or compressed, X is 0. If you extend it, let's say, by 10 centimeters, X is 10 centimeters. And so other types of energy?
Kinetic energy.
Kinetic energy, yeah. Kinetic energy, let's say 1/2 mv squared. Other types of energy, did we talk about any other? Yeah.
Rotational potential energy.
Yeah, oh yes. Oh yes. Rotational kinetic energy. Rotational kinetic energy, 1/2 moment of inertia times angular velocity squared. Other types. So this is rotational. Other types. Yeah, we talked about thermal energy, but we don't have a real good formula for thermal energy that's more universal. So for the moment, we can forget about it. So it's pretty much a complete list of energies that we encountered so far. Notice that all the types of energy that we interpret as potential energy depend only of the position of the object or mutual position of the two objects in this case, only position dependent, while the kinetic energies are velocity dependent. Okay, there is a kinetic energy can be is it possible kinetic energy to be negative number in the formula? Anybody? Is it possible or not?
I don't think so.
Why?
Because, I mean, if you have a velocity going backwards, that's not negative velocity, it's just a different direction.
Any velocity, well, here in this formula, instead of velocity, we use, well, no vector sign, it is practically instantaneous velocity or speed, instantaneous speed. It could be positive or negative, but you're squaring it. So V squared is always non-negative. Masses are only positive. 1/2 clearly is positive. So kinetic energy can be only positive number or 0 for the case of an object that is at rest. V equals to 0, or massless objects, we don't have massless objects around us. So what about rotational kinetic energy? The same story, positive or 0. Well, what about elastic potential energy? positive or zero, cannot be negative. What about gravitational potential energy? H could be negative, right? It could be, if I take the 0 point, the zero height to be, let's say, the floor, if this object is located on the somewhere in the basement, H is going to be a negative number. Or if I take the 0 point to be the surface of this table, H is positive here, let's say, and H is going to be negative if the object is under the surface of the table, right? Below the surface. So the presence of negative electric potential energy is perfectly fine. We just have to, you're going to see that we have to use. So look, electric potential energy describes the energy between this charge, point-like charge here, another point-like charge Q2 here, the distance between them R. And this energy, you can think about this energy as if this energy is stored in this and this object, in this and in the two charges, in those 2 points. Or alternatively, you can interpret this formula as if it is telling you that this energy is stored in the configuration of the two charges, in the space around the two charges here. So those are two alternative ways of looking at the same thing. Well, if we have a formula for electric potential energy of configuration of two electric charges, you may ask the question, how would the electric potential energy of configuration of 3 charges looks like? So let's say that you have, let's say, a charge Q1 here, charge Q2 here, and charge Q3 here. What is the electric potential energy of this system of 3 charges? Well, you can demonstrate using the same procedure as in the case of 2 charges. You can demonstrate that the energy stored in this system of 3 charges is given with the following expression. So let's say that the distance between those 2 charges is R12. The distance between those 2 is R13, and this distance is R23. In that case, you can show that the electric potential energy of this system is equal to K times Q1 times Q2 divided by R12 plus K times Q1 times Q3 divided by R13 plus K times Q2 times Q3 divided by R23, I guess. In other words, you take each pair, each possible pair of charges, and you write the same formula. You add up the results, and you have the total electric potential energy of this system. And again, you can think about, let's say, those 3 charges, the total potential energy, let's say, could be what, 6 joules. You can think that those 6 joules are stored in some fraction of those 6 joules are stored here, here, and here. Maybe in some proportion. Or you can think that those 6 joules are everywhere in space around the system. We're going to talk about, again, the location of that energy. We're going to discuss it again at the end of this chapter. Let's see questions and remarks so far. Okay, now. Right, probably every time when people don't have questions, I probably should come up with my own questions to encourage you not to fall asleep. Basically, it is 1:30 shortly after lunch. You have lunch, and after that you fall asleep. It happens to anybody. May happen. Right, to prevent. Not that I want to put you in a state of sleep deprivation, but yeah, okay, yeah. Go ahead.
So I guess the sum or the total electric potential energy in the system that you drew up there
Uh-huh.
is just the sum of the electric potential energies for each. Or
For each pair, yeah, you have to do each pair separately. But look, this thing, if you have, instead of 3 charges, if you have 5 charges, now writing the pairs is going to give you many more terms, right? In the case of 5 charges, you're going to have 10 terms. And you see that the number of terms increases very fast. So, well, in cases when you have large number of charges, maybe like the case when you have, well, certain number of excess electrons, maybe stored here, let's say, excess, right? So that the object is not electrically neutral, but charged with negative electric charge due to large number of electrons. If you try to write the total energy of that system in this way, so if you have, let's say, something like a Avogadro number of electrons, excess electrons here, the number of turns is going to be, what the Avogadro number is 10 to the 23. We're going to have 10 to the 46 terms of this type that you have to write. 10 to 46. You can keep writing for the rest of your life, and you won't be able even to write a single, well, even a fraction of those. So we need alternative form of writing electric potential energy. And well, in this course, we're not going to consider other alternatives, but instead, we're going to introduce another important concept that is going to allow us to write the electric potential energy of an object in an alternative way and actually make everything simpler. And how to do it? Well, let's say again that you have 2 charges. One charge is here. And let's say you have a second charge. Q1 is here, Q2 is here. Maybe this one may be fixed in space, pinned down so it doesn't move, but this one I bring it to certain distance. And the electric potential energy of this configuration is going to be, let's say, 6 joules. The ratio of the electric potential energy of the system divided by the value of this charge, Q2, is what we call electric potential and I'm going to use the letter V for that. For that concept. So electric potential is energy per unit charge. The units for electric potential, therefore, should be joules per coulomb. And joule per coulomb we call volt. So alternative name, volt for joule per coulomb. And similarly, well, look, now we have many electric concepts. Electric field, VE, electric potential, energy, and electric potential, everything is electric and sound pretty much the same way. So very often, instead of electric potential here, I'm going to use the term voltage. So here is my pins down source charge, and here is my second charge. The energy of this configuration divided by how many coulombs this thing is gives me the voltage at this particular position. If I move the second charge here, well, the electric potential energy changes, and therefore the voltage, the electric potential changes. So at every spot around the source, I can assign a value of the electric potential at that spot. And I'm going to create practically this way a map of the electric potential created by the source everywhere in space. And this should remind you to the map that we talked about when we talk about electric field. So you have a source. The electric field is an arrow that you attach to every single point in space. The magnitude of that arrow is given with this formula, if the source is point-like, of course. And the direction we describe with words, away from positive into negative. Now we have alternative description of the same electric phenomenon. Again, the same charge here, but we just created a procedure to attach not an electric field, but voltage at every point in space. And that procedure gives us alternative description of the same space, electrically charged field. But of course, the description in terms of voltage, the description in terms of electric potential is simpler because a scalar, a single number, is simpler object than a vector. So here it is. Let's draw the two descriptions. Here is a point-like charge, let's say positive, and the description of the electric phenomena generated by this source charge Q is you attach to this point a vector like this. You attach to this point a vector that has to be like this. Maybe a point like here is you attach a vector that is like this. A point that is closer, maybe here, you attach a vector like this. This is one description. Here is one vector E1, E2, and so on and so forth. The alternative description in terms of electric potential voltage would be, well, instead of this vector, you put some number of, let's say, 5 volts here, 5.1 volts here, 8 volts here, and so on. To every point in space, you attach a number, the voltage at that particular spot. Now look, if you combined the formula for the definition for electric potential energy with the definition for the voltage. In other words, if you substitute here the energy between of a configuration of two charges, look what you're going to get. You're going to get K times Q1 times Q2 divided by the value of the, divided by the distance. All of this divided by Q2. And Q2, of course, cancels out. And the result is K times Q1 divided by R. This is the voltage V at a distance R from the source Q1. So that voltage could be positive number and negative number, depending upon the value of the charge, the value of the source. Is it positive source, positive electric charge, or negative electric charge? Now, we have a little bit of a problem in a sense that, well, the problem actually is familiar from the first semester. What is the gravitational potential energy of this piece of chalk? Let's say this piece of chalk is 0.1 kilograms. What is its gravitational potential energy? Anybody wants to do a quick calculation? MGH? Anybody? Brownian points or real brownies? What is the gravitational potential energy of a mass of 0.1 kilograms located right here? You cannot multiply. You can use calculator, yes. So 0.1 times what? 9.8, yes. Times
Two-ish,
how much?
two-ish meters.
2 meters
Ish.
with respect to this. So what number do you get? So you get approximately 2 joules. But what if I tell you that you have to take the zero height to be at the level of the table? In that case, you're going to get, instead of 2 joules, you're going to get 1 joule. If I tell you, you take the 0 point at sea level, you're going to get you're going to get something like 1,500 joules. So the value of the gravitational potential energy depends upon where you have selected your 0 point. And of course, in the first semester, we did some calculations using the gravitational potential energy. And this arbitrary selection of the 0 point didn't bother us so much, because in any problem that involves gravitational potential energy, it appeared as a difference of 2 gravitational potential energy. Gravitational potential energy at this minus gravitational potential energy at this position. No matter where you choose your 0 point, the difference is only going to be proportional between the distance to the difference of the 2 heights. And no matter where you choose the 0 point, the difference of 2 heights is going to be the same number. So, in the definition of any potential energy, you have a level of arbitrary choice. So when I tell you that this piece of chalk has 1,000,000 joules of gravitational potential energy, That's perfectly fine. I have selected the 0 point somewhere. Who knows where, somewhere far away. The same thing happens in the discussion of electric potential energy. And well, look, the voltage is electric potential energy divided by per unit charge. If I have a level of arbitrary choice for the selection of electric potential energy, I'm going to have also the same level of arbitrary choice for the selection of the voltage. So we need some convention in order to remove this arbitrary selection of your 0 point of energy. And the convention is that the voltage of the planet Earth, the voltage of the ground, is taken to be 0. This is the convention that we use. Actually, alternative convention, which is exactly the same, is to take the voltage at infinitely distant point to be 0, infinitely distant from us. So it is the same thing. The ground is closer to us, so we're usually going to think about ground, but it is the same thing as the voltage to be 0 at infinitely distant galaxy somewhere far away from the source. So what we need to remember from today's introduction of new concepts, probably the definition for electric potential energy of a system of 2 charges. This is sufficient. We don't need the 3 charges configuration. And the second definition of voltage, but most importantly also the voltage at position R, at the distance R from the source Q, is K times the source divided by the distance. The voltage created by a charge Q1 at a distance, at a point that is separated by a distance R from that point charge. K is the same constant of proportionality that first appeared in Coulomb's law. Now, let me. I used to have a prop here, but I can always find the prop right there. Here's battery. I've seen batteries like that. How many volts is this battery? 9. Okay. What is the voltage at this point of the battery, at this terminal of the battery? Let's see. Is anybody going to give some? When I'm asking questions like this, there are no wrong answers. Yeah. So this point 0.
It's not conducting.
Well, we don't. Well, 0 is perfectly fine answer. Anybody else try to? So your argument was that no currents, 0 seems a good choice. But if it is 0 at this terminal of the battery, what is the voltage at the other terminal? What is the potential at the other terminal? 9. Okay, good enough for me. Yes?
Is it 4.5 volts?
Yeah, that's more symmetric choice, right? You like symmetry, you say, like in any democratic system, you may have equal number. Well, one of them negative 4.5, the other one positive 4.5. Again, the difference between them, 9. Good. Any other choice? Well, if you selected the 0 at this terminal, why didn't you select the 0 at this one?
Like, I didn't think, forgot that I was able, it's not 9. But I was just thinking like one side would be like neutral and the other side would be the one that gives you the charge.
Yeah, well, you can, actually this is technically reasonable because is anybody here driving a truck, pickup truck? Yeah. So in many trucks, the terminal of the battery under the hood is connected to the chassis of the truck. I don't know how is your truck, but in many cases, this is what they do. In other words, they connect one of the terminals to ground practically, in many cases, which fixes the potential, the voltage of that terminal to 0. This is our convention. Ground is 0 for us. So this is perfectly nice choice. So look what is the situation with this arbitrary choice of the 0 point. I can perfectly say that the potential of this terminal is 1,000,000 volts. But this is going to force me make the potential of the other terminal 1,000,009 volts, so that the difference between the two potentials to be exactly 9 volts as it is. In any practical application, the voltage, the electric potential is going to appear as a difference of the electric potentials between 2 points. And therefore, where you have chosen the 0 point doesn't matter. In the formula that is written right here, the 0 point is implicitly selected to be at infinity. And where r, the distance r from the source, is infinitely large, the voltage, this formula tells you the voltage is going to be 0 at infinity. So the conventional choice is selected here, and I wrote the formula without describing you the process of integration that led to this selection. What matters is that the physical meaning is only a voltage difference between 2 points. The voltage at point by itself is meaningless. So when I say that, I can charge this Van der Graaf with very large charge. And when I say that the voltage on the surface of that Van der Graaf is 10,000 volts, I mean that the voltage difference between that metal sphere and the ground is 10,000. Or the voltage difference between that metal sphere and the infinitely large, infinitely distant point in space somewhere in a different galaxy, that voltage difference is 10,000 volts. So physical meaning is only in the difference between two voltages. So we're going to continue next week with capacitors. We're going to connect the amount of charge on a capacitor with the voltage difference between the two plates of the capacitor. And after that, we are going to talk a little bit more about energy stored in electrically charged configuration of charges from a different point of view. So again, please spend as much time as you can and more on chapter 19. And by the way, when you're reading, you're going to encounter unclear statements. write them down because you're going to forget about them if you don't write them down. Write them down and let's discuss them next time. If you don't have questions, I have quiz questions on my laptop. So this is a treat, yes. Have a nice weekend.
Somebody asked, when will the practice exam be posted?
Oh, practice exam. I'll post it, I'll write a practice test at least a week before the test, at least 1 week before that, probably more. So you have homework problems so far, work on the homework, and this is going to fill your time. Thank you.